Mr. Navarro is a condition-based maintenance consultant who has recently retired after 38 years of service from John Deere Construction and Forestry, headquartered in Dubuque, Iowa. His experience is highlighted with management positions held and product support roles throughout the world. I'm going to turn this over because his presentation is a little bit is long and complex, and I want to do it justification.
Thank you for having me here. Thank you to Dennis. And you have a double challenge today. You will have to pay attention to this complicated subject and also try to understand me. So I'm glad to be here, and thank you very much for your patience and your time. The machine is talking to us, but are we paying attention really? If you look at all the signals we can get from machines today, there's a lot. Machines became very intelligent. They send messages through telematics, through fluid analysis, through inspections. Even the operator supplies us with information. If you multiply the number of machines you have and the amount of information coming from the fleet, it's very hard to manage the amount of information unless you have developed an automated system to interpret that. If we think about the gross information, how can you make it much more powerful when you combine the information coming from the machine to the information coming from the lab and the information coming from the technician after the inspection. At the end of this presentation, I'll show you some of the correlations or the messages you see there. Most of them, many of them are related to fluid management. So my agenda today is to show you the changes in technology and how the fluids have changed as well, and show you that fluid analysis is a very underutilized tool. I suspect everybody in this room uses fluid analysis. Is that the case? Are you satisfied with what you get from fluid analysis? Are you getting your money back from fluid analysis? It's a powerful tool, but we are not getting the money back, and I'll show you a little thing about why. My expectation is that you get acquainted with these changes and that you measure the challenges, and when you go back, think about what you saw today and try to implement, not all of them, some of them. Try to figure out how can you get better results from your fluid analysis. The first part will be show you the changes in engines and oils. I'm going to talk a little bit about coolants, the hydraulics and fluids, fuels, and very little about DEF because there's not a lot of issues we need to talk about it. My second part, I will show you the tools, oil analysis, coolant analysis, fuel analysis, inspections, and how to cross that to telematics. So what has changed in engines? Let's talk about engines. We have right now, we're in Tier 4, and the last 16, 17 years, we have seen changes manufacturers thought it was impossible to accomplish. The first stages of changing engines into emission engines were very scary, but manufacturers learned, and today they believe they can do it much better, but at the beginning, was scary. Most of them started the changes by moving the first piston ring to the top of the piston to eliminate any empty spaces that will produce some emissions in the combustion. The same pistons were later manufactured of two different metals to resist the heat that was being generated. Then we learned about the cool EGRs. EGRs are supposed to get back some of the exhaust gases into the engine, so we reduce the amount of oxygen. With this, we accomplish less nitrous oxides. And then needed to be cooled so you recover the air mass and you recover the power for that engine. Then we had the variable geometry turbochargers replacing the wastegates turbochargers just to be able to provide enough air at different engine speeds. Twin turbochargers as well. Then fuel filtration. Fuel is being injected at high pressures. You needed to clean those very small limits. Then you have serious turbocharging to really improve the amount of air you provide the engine at different speeds. Then you have the high pressure common rail that injects the fuel 12 times higher pressures than maybe 12 years ago at a very high speeds. Then you have the increased power in controller capacity. Thanks to controllers, you can do a lot of things with pilot injection, ramp pump injection, multiple injections. So you are squeezing the power of those engines using all kind of tricks and devices. We are asking those engines to burn faster and still produce the same power, but with an exhaust that's cleaner than the air they suck. Finally, the addition of all the diesel particle filters and catalysts and after treatments makes those engines extremely complicated, and we are going to see why also makes maintenance more difficult. Pilot injection, as just mentioned, is feasible thanks to electronics, and what the industry is looking at is produce an stoichiometric combustion where you don't have a lot of fuel left or too much air not used. So you have a perfect match air fuel, and for that reason, engine run much harder now, but much cleaner. Engines breathe better through additional valves, revised camshafts, better turbochargers. So the rooms for mistakes have narrowed. We don't have a lot of room, especially on temperature. The overheating tolerance is minimum today compared with the past. TBN on the oil versus TAN has narrowed. They are running very close. And fuel cleanliness, we have no option but to run very clean fuels. Fluids have changed as well in order to cope with these changes in engines. Oils contain less TBN and still need to protect the engine and be stable and provide oxidation resistance. What else we have? Oil. Oil has been used now, is being used as a coolant. These new engines have almost double the amount of flow in the oil. The sumps are larger, oils, pumps are larger. We're using oil as a coolant. Coolants, because of the added heat, needed to be different. Now organic acid coolants is the norm. And fuel is injected at very high pressures and at the speeds that exceed more than 1,000 miles per hour. Can you imagine that? So what injector is going to resist that? If you have any contamination at those speeds and pressure, you cause erosion. You also have high temperatures, you cause carbon deposits and varnish. All those challenges. So fuel needs to be extremely clean more than hydraulic fluid. Dilution could happen. Fuel dilution is a byproduct of technology. You cannot avoid it no matter what you do to your engine. And fuel relies on additives to protect the injector and the injection system. Not in the past. In the past, we run fuels without any additives almost. Today, we depend on additives. And soot could be also a byproduct, depending if you work in a high altitude. So the rules of the game in maintenance have changed. And sometimes we forget about it and we keep doing things like in the past. DEF, diesel after treatment, fluid is also in the game, and we need to think about it. So when you talk about oils, the TBN has dropped. Oils today have less TBN, and we're supposed to change oil before the 10 or the acid number exceeds the TBN. So new oils have less TBN. So we have less room apparently, but remember, fuel has only 15 parts per million in sulfur, so we compensate on the other side. So basically, you can run the same hours with the same oil today thanks to that new fuel. But since these new oils start much less TBN, today we have 9 TBN with the new oil compared to the old ones at 12 or more. You have to keep an eye on the 10, because if the 10 exceeds the value of TBN, you will have metal generation, and you will scratch your head, where's this metal coming from? Why? Why is that coming? There's no dirt, there's no fuel. What's causing that? You need to check 10. And 10 was reserved only for hydraulics. Well, now you may have to use it for engines as well. That's the new game. When we talk about coolants, nitrate-based coolants were okay for the past, and it helped us run engines, heavy-duty engines, and protect cavitation from cavitation. It worked with an anodic principle where we created in the yellow stripe there like a protection for the liners. Well, that is not good enough with current engines. We need to go to organic acids coolants, where we call them cathodic. What it does is transform the ions, change polarity, and use those ions to patch the holes, like when you patch a hole during the winter in the roadways, potholes are patched in the liner like that. So new coolants provide that protection. The question is, can you mix them? Can you mix them? My advice is don't mix them, because you diminish the protection of the new coolants. It's better than you adopt the new coolants for the whole fleet. So application has an impact. If you have a tractor or a truck that has light loads or long idling periods, it's going to have an impact on dilution or soot. Engines need to perform in high altitudes as well. You could have machines that do intermittent work or continuous load. The results in oil analysis are going to be different, even if they are similar machines. I mentioned they could have fuel dilution. They could have soot, which is worsened if you work in altitude or you idle a lot. So when we talk about consequences of liner cavitation, cavitation comes from bad use of coolants. Coolants do not protect against cavitation. Or you could have soot, like the pictures are showing. You could have piston delamination from high heat. Delamination doesn't happen every day, but if you have a plugged air filter, you increase the temperature in the combustion chamber, and you could cause that kind of issues like piston delamination. An injector failure by carbon buildup or varnish is part of the game. If you remember the temperatures, if you don't use any additives, that could happen. Injectors are not lasting like in the past. So what are the areas we need to look for engines? Temperature is a critical one. Air filters, we don't have room for dirty air filters anymore. Check for TBN and TAN. If you don't use TAN today, try to use it because you are going to need it. Coolant types, remember the new type of coolants based on organic acid, long life coolants. Water harness. Remember water. The water we drink, this water, is good for human consumption. It's not good for engine consumption. If you test this water, it will have a harness that is not good for the engine. We assume everybody is using pre-diluted coolant, but if you mix it locally with water from the top, you are not helping your engine to survive. Depth quality and contamination. We have to keep an eye on the depth quality fluid you use and whether or not you have mixed it with fuel or coolant. Fuel type, we mentioned that. I'll talk more about it. Watch for fuel dilution, coolant leaks, soot and dirt contamination. Especially coolant leaks are bearing killers. Coolant is the worst contamination you can have in an engine because you can lose an engine very fast. Watch for critical metals generation and watch for acid number. Now, I'm going to switch gears to pass to hydraulics. Hydraulics, I'm going to discuss it similarly with the changes in hydraulics. We don't talk about Tier 4 hydraulics, but hydraulics have changed anyway. And the changes are that we use smaller reservoirs. That's the fact. We need space in machines, so smaller reservoirs. And what's the problem with a smaller reservoir is that you have less time to release the air and you have less time to cool the fluid. But we have also controllers, electronic controllers in hydraulics that follow the torque on the engine very closely. It means that the hydraulic system really sucks the whole power available from the engine. High pressure tandem pumps, they are running at very high pressure, over 6,000 PSI. What happened with that? The competition to have the strongest machine in the market, the strongest arm and boom that can break the soil very easy, put a toll on arms and the structures. So the key is making the arm to last longer with those powers. It's a challenge for manufacturing because hydraulics are so powerful that to keep arms without breaking is becoming a challenge. The use of attachments like hydraulic hammers, very popular. Remember, if you use the same hammer with different machines that use different fluids, you are already cross-mixing them. You are already causing issues to both machines. And hammers usually are left in the open with the hoses on the ground without protection on the connectors. And new fluids are becoming popular, environmentally sensitive fluids, biodegradable fluids, all-season fluids, fire-resistant fluids. None of them are mixable between them. I mean, these are supposed to run by themselves. So what things we see in hydraulics? Increased pressures, smaller reservoirs, more environmental concerns with fluids, electronic controls, more power, and the room for mistakes in hydraulics has also diminished. We don't have a lot of room. These systems do not allow fluid cross-contamination. If you mix two different kind of fluids, you will have to pay for it. Water tolerance in these pressures is minimum. Running at 6,000 PSI and close to 120 Fahrenheit, if you have a little water, more than 1,000 parts per million, you have a challenge. You have a challenge with your pump. And you have to look to watch for temperature as well as for water content. These fluids I just mentioned, they need to release air in the time they have. You see the fluids usually stay in the tank only 20 seconds, so it changes the complete volume in 20 seconds. You need time to release air and time to cool it, so you need to keep radiators very cool, very clean. Needs to be very clean because of the high pressures and closer tolerances. And the fluids need to resist those temperatures. And if you mix them, you are changing the nature of those fluids and you are creating a new product. New fluids are becoming the norm in certain areas. They require biodegradable. Biodegradable are very tricky to handle. They don't take water easily. And it's hard to keep water out unless you use a bypass filtration. They are zinc-free fluids today. They are biodegradable. They are all-season fluids, and they are fire resistant, and there are even more types of fluids being used. When we talk about viscosities, machines can run on any kind of fluid, but the limiting factor is temperature. What's the season? Engine oil works, but engine oil is very heavy. In cold weather, it doesn't work. And also, they lose viscosity very fast. You can have challenges with cold weather when you use engine oils or tractor fluids. So hydraulic fluids like 46 or 32 are very popular because they are very stable in viscosity loss, as the graphic shows it. When we talk about application in hydraulics, they need to perform in very cold weather, like the northern part of the United States or in Canada or Alaska. They need to cope with the high loads. They need to cope with humid conditions. If you do dredging or work close to the sea, you have to have a system that can handle hydraulic attachments like hammers, but also corrosive environments like you see in that last picture. All of those environment situations get into the hydraulic system through the cylinders. No matter how sealed they look, you will get humidity and contaminants within the system. You need to protect the heart of your system, and the heart of your system is the hydraulic pump. Hydraulic pumps usually have bronze alloys, and they can fail for many, many reasons. At least I can list at least 12 reasons. So when you look at your oil analysis, look at copper generation, because that is the heart of your system. In this picture, I'm showing a failure by etching produced by the lubricant, a lubricant that's very aggressive for the fluid. In the right picture, you have pitting produced by water. So they look alike, but they are different. And as said, there are at least 12 reasons to produce copper, and copper is coming from the pump. Well, we look at areas we need to be looking at, keeping an eye on hydraulic systems, keep an eye on mixing, don't mix fluids, watch for the signature in oil analysis, watch for copper readings because that's the life of your system, watch for water, use the Carr-Fisher test. I'll talk about a little bit about that later. And be careful with attachment, especially hydraulic hammers, compactors, because of cross-contamination. Let's talk about tools. But the first thing about oil analysis is standard deviations. If your lab has not calculated your wear tables, what are you getting is perhaps you are getting too many warnings, or maybe you are not getting enough, but you are not getting the right amount of results to you. The median values in the calculation of standard deviations, Excel sheets can do that for you, but your lab should provide you tables, wear tables for you based on the standard deviations. In the example, 68.27% falls within one standard deviations, one plus and one minus, in total 2 standard deviations. That's how wear barrels behave. They produce that curve, that's a parametric curve, and usually we use that kind of calculation for wear metals. Other indicators are not used with or calculated that way, only wear metals. And what happens if you don't have tables? Every machine is different. Even if you have machines working side by side, if they don't have the same engine, working the same condition, doing the same stuff, you may need different tables. I mean, they are not identical engines. Engines have different oil sump capacities. They have different kind of injection. They have different controllers. They have different camshafts. So if your lab is using one single table to judge your whole fleet, it means you are not getting back your money for your oil analysis. In this example, I have two machines, an 800 Hitachi and a 270D John Deere. The numbers are different. If you look at the numbers, iron is totally different. Lead, copper, all of those are different. That's why different machines require specialized and individual tables. Your lab needs to calculate those for you. You won't get your money back. Or the numbers mean nothing to you. You may be worrying too much, or maybe you don't get the right report when you need it. So my advice, do your lab have those tables calculated for you. When you have the oil analysis results, your lab can group them by critical or abnormal or normal, different types of warning levels, and that allows you to address the ones that really need care. But you need to calculate your tables. You need to have them ready for you. Otherwise, oil analysis won't work for you. In this example, this is an engine with oil results from an engine that has a coolant contamination. I know that's a coolant because of the constituents. You have sodium and potassium, sometimes silicon from the coolant. I know there is coolant, so the labs know about this, but sometimes it's a little more complicated than that, and labs can be it's somehow limited by the time they have to give you results. You see, a lab analyst possibly makes a basic salary and is allowed 40 seconds to test, to give a report. So how much are you going to get? You pay around $10-12 per oil analysis, and then you have a guy that has only 40 seconds to give you results. He's not going to spend a lot of time analyzing your results. Oil analysis is a powerful tool. I know there is coolant in that sample, but I can also know where the coolant is being leaked. I can find the source of the leak with oil analysis. In this example, there is a coolant leak, and I also noticed that the copper is minimum. That is telling me that possibly the leak is through liner speeding, not through the oil cooler. So oil analysis is a very powerful tool. If you have high copper readings, like in this example, I can assume the oil cooler has gone bad, and I'm having a coolant contamination through the oil cooler that has failed. I also can have a coolant analysis, like in the lower part, that also confirms the presence of copper. That tells me the oil cooler went bad. So oil analysis can do much more than you can imagine, but it's a tool that requires a lot of knowledge. I don't know if the labs are going to develop the knowledge, but you have an option, that is, you can develop the knowledge. Because coolant, determining if you have a coolant leak, the question is it glycol or is not a glycol? Because coolant, which is made of sodium and potassium, where sodium could be coolant, could be dirt, could be salt, and potassium could be coolant as well, fertilizer or soap, where the answer is difficult, right? And you think for $10, your lab is going to tell you exactly what it is. They know the basics, but they don't take the time to go through this flow chart. Through this flow chart, I can determine that that's in fact a coolant leak. I can determine if the leak is through the oil cooler. I can determine it's through liner cavitation. I can do a lot of things with a flow chart, but it tells me step by step what those readings mean. If we jump into dirt, we will have the same situation. So the sign down there is exactly what I tell you. is you're not going to the trouble of interpreting this for you. The next one is dirt. Dirt or not dirt. Because dirt is represented by silicon and aluminum. But silicon could be dirt, silicon gasket material, it could be anti-foam additive from the oil, it could be coolant silicate. So the interpretation becomes more difficult. And aluminum could be piston material, it could be dirt. So how do you interpret the results? Well, you also have a flow chart that can be used. A flow chart can tell me what is this sample I'm getting. Is dirt? Is gross dirt contamination? Is silicate from coolant? Is silicon from gasket material? Or is a foam inhibitor? This flow chart helps me to determine that. I'm not trying to turn you into an expert oil analysis interpreter. I'm just showing you the power of this tool. So labs are not going to go into deep interpretations. A couple of them go beyond the call of duty and do a good job. Most of them are very precise in what they measure, but they don't have the time to go through this kind of explanations. When we go to an hydraulic oil or hydraulic fluid analysis, there's a lot of things you need to know. Like in this example, is the copper readings normal? Is the silicon readings fine for this sample? If I don't have sodium, if I don't have aluminum or potassium, I need to know my fluid. That fluid on top shows that is a Shell Donax TD product. And I know it has a lot of silicon, which is a foam inhibitor. And also notice that particle counts are very high. Why am I having high particle counts? If there's no dirt, why do I have high particle counts? So there's a lot behind the story. And we can know that particle counts are by themselves a whole science. When you send your sample to the lab, little jar, what you get back in metals and contaminants is only up to 6 microns in size. That's what the tools, the lab instruments can interpret. When you move in size, they are hidden. You don't see them until they're big enough the human eye can see them, provided there's a good background. That's why we do particle counts, as you can see down there, because we can see from very small to very large with particle counts. But particle counts can be tricky because a mixed oil will have high particle counts, but you won't be able to interpret easily because it's not dirt what's causing high particle counts, but gels. So this is the range of visibility to particles. What about water? Water is very hard to see. Most of the labs offer the infrared test, and you pay for that. It's very cheap, but the visibility to water starts at 1600 parts per million, the infrared. So if you have less than that, you don't see it. And if you have a hydraulic pressure system that has 6,000 psi, and you don't have visibility to water up to 1,000 parts per million, you are missing the boat. You are paying for nothing. You are not getting the visibility to the results. The coefficient by co-distillation is the answer. Obviously, there are all the tests to check for water content, like the crackle test or like the humidity sensor. But those are measuring only dissolved water, not total water. So you have coefficient by co-distillation as the answer for that. Most labs use the infrared, and you won't have visibility. The critical level, you are missing the critical level if you don't do coefficient by co-distillation. When we talk about dirt, dust, and water, this is an example, an hydraulic system where I have dirt confirmed because you have silicon, aluminum, and the ratios to 4:1. is dirt. And also, in this sample, I have plenty of water. And if you don't have Carl Fisher, you won't see this water. That's the beauty of the Carl Fisher test. And the high particle counts could be a mixing issue, or could be dirt. But particle counts are telling you, in this case, the numbers are 25, 25, 23, which is an atypical number, typical from a sample that has plenty of water. When we talk about mixing or fluid compatibility, I have in that chart with colors hydraulic fluid, zinc freeze, I have hydraulic zinc base, universal tractor fluids, ATFs, engine oils in 2 different viscosities. As you can see, the no's are abundant. It's telling you you're not supposed to mix them. Remember, each fluid is developed through years of experimentation, and if you mix them, you create your own instantly, and it won't behave like you want it. When I talk about mixing, I mentioned the formation of gels. That's what happened. You create gels that reflect in particle counts. High particle counts could be gels, and the numbers are atypical. You can see in 2 different fluids. I have examples of what you get. When you have water, you have equal numbers. They are supposed to have 2 different code numbers and not 22, 22, 22. That's an issue when you have water in the mix. Let's jump to coolants. This is an example of coolants. You have to measure your additives and you have to measure your water. This is a real example from a case I saw. This engine was suffering from corrosion, aluminum corrosion, and the results showed that he had no protection from the organic acid side of the results, and the pH was very high. The higher the pH, the more corrosive for aluminum the coolant is. So you have to test those. And you also have to test the water. I mentioned the water that we drink is okay for humans, it's not okay for engines. You look at the results of that engine, the chlorates were very high as well. And if you look at the OEM versus ESTM specifications on what they want on chlorates, sulfates, and dissolved solids, those are the numbers. And you can test those locally. I can test those for you in 1 minute with a 3-way stick, and they are very cheap. So you can test your water, but you can test your coolant with 3-way sticks, and very easy, very cheap. And you know if you have the right concentration, if you have the right amount of organic acid additives, and if you have the right pH. When we talk about fuels, perhaps fuel samples are the worst investment because you don't get what you need. And the problem starts with yourselves, because when you send a sample, you send a sample that you took from the wrong place at the wrong time. And I explain it to you. When you took your sample from your tank, your bulk tank, you need to take the sample at certain heights and do the refueling after refueling. If you do it after refueling, do it at the middle of the tank. But if you are not doing after refueling, you have to do it in 1/3 below. Otherwise, what you're sending to the lab could be crap. The lab will tell you this is good for nothing, or will tell you your fuel is clean. Okay, that's the problem. Catching the ghost, that's your task. Be able to catch a sample that is representative of what are you feeding your tractors or trucks. With machines, what happens? The fuel gets cleaner as the machine works during the day, because 60% of the fuel that's not used by the injectors goes back to tank and is filtered again. So at the end of the day, the fuel in the tank is very clean. If you take a sample at the end of the day, what's the lab going to tell you? It's going to tell you that your fuel is very clean. So take the sample at the right time. Catch it, collect the sample in the first hour of operation, and you can take it at the middle of the tank and let the lab know where did you take the sample. But still, you have to do fuel analysis because you could have bacteria, you could have a lot of particulate, you could have high sulfur fuels. It's funny, but still show up from time to time high sulfur fuels. You need to know your cetane index for easy starting in cold weather or high altitude, and you need to know how much of biodiesel is in the fuel. You also need to know if you have a contaminated fuel. In this case, this fuel shows a cetane index of 69. Wow. With 69, you will burn that engine like a jet. That sample comes from a diesel fuel that was contaminated with gasoline. I mentioned that fuels are no longer able to run by themselves. They need help. They need additives. You can have an additive that has lubrication and dispersion, oxidation inhibition, and all that. But you also have additives that are very strong solvents for engines that have already developed some kind of issue with injectors for varnish or carbon deposits. Those strong cleaners help clean the injector, but think that an injector that's already producing or giving problems is very hard to save. When we talk about DEF, the diesel exhaust fluid, most of the issues come from mixing or filling the tank with the wrong fluid, but you also could have particle contamination. These issues, what happened with these issues, that could be very costly because it will poison your catalyzer. That's the issue with these mistakes. Finally, inspections. Are machine inspections done in time? Are you checking the right areas? Are you uploading inspections to machine maintenance application? Are inspection crossover oil analysis? Inspections are very powerful, provided we can interpret that and cross information. Like you have in these pictures, a leaking roller or a propel motor full of dirt. Those are reportable things that you need to know. The propel motor that's covered with dirt won't cool down as necessary. So that's a report that needs to be recorded someplace. And telematics. Telematics is very powerful. Get power utilization, get high temperature occurrences, and cross that information with fluid analysis. Cross inspection results, telematics, fluid analysis. Telematics is a very, very powerful, provided we can interpret the data. So the new challenges is deeper knowledge on machine health interpretation is needed. We cannot continue doing what we have accustomed to doing. And there is a new rules in the game that you are expected to play, and that's something we cannot change. The opportunities is a better fluid analysis interpretation from labs and users is a must. The right wear tables. Think about wear tables. How to have the right tables that tell you the truth about your equipment. Better use of telematics. And boost the power telematics by crossing it to inspections and fluid analysis. To finish, remember, a machine is talking to us. You need to learn the correlations. The torque converted lockup is sending fault codes. Well, the transmission shows high aluminum in the oil analysis results. The brakes are chattering. The differential oil lacks limited slip differential additive. There is a leak in the boom cylinder. The hydraulics have high particle counts and dirt. Inspection reports high oil levels. The engine is having oil dilution beyond high percent. Telematics show high idle utilization. The engine is developing soot. The engine oil appears milky. The coolant pH is too high and it's low in organic acids. You have a coolant leak. I didn't have more space in the picture. I could put hundreds of those correlations. I just put those to show you that the correlations mean a lot, and we need to better use those correlations and learn those tools to really make fleets more usable or extend the life of equipment. With that, I thank you for your patience with me. I run very fast through complicated subjects. Thank you for your time. If you have any questions, I believe this zoo is waiting for us.
We have time for a couple questions. Anybody have any questions? A lot of material was covered. Thank you very much for sharing with us.
Thank you.